principle with very elegant sample complexity bound, right? But that results were derived when we assume our classifier, learned classifier, is always consistent with the training sample. In other words, your learned classifier, your learned hypothesis space, hypothesis, zero training error. And then we can show that when the number of training examples m is bigger than some lower bound, we can guarantee that with high probability, 1 minus delta, delta is the confidence level, our learned hypothesis will have true error less than the designated level epsilon. Right? So as long as, so let's review this conclusion again. Right? So when your algorithm, or learning algorithm, chooses a hypothesis space H and is powerful, in that for whatever training data, you can always find a hypothesis with zero training error. Then we can guarantee with probability at least 1 minus delta, the true error of your learned hypothesis is less than epsilon if the number of the training examples is bigger than this bound. This bound obviously is some function of epsilon and delta, the error levels, the error and the confidence levels. So this is what we have seen so far, right? And I believe this is important for you to finish a few problems in homework too. Right? You need to use this bound to justify some particular learning algorithm, like the same trees, whether you can path learn some particular Bloom function. According to path learnability, you have to show the number of samples is polynomial to like number of examples, size of hypothesis space, etc. But when we look into this result again, we find that there are underlying assumptions. The first assumption is the training and test examples come from the same data distribution. This is actually the assumption adopted by almost all the problems in computational learning theory is reasonable. When you conduct learning procedure, you always assume that your test examples are sampled from the same distribution as training examples, and otherwise, why do you conduct learning procedure? But the second assumption is kind of aggressive. What is the second assumption? To achieve this sample complexity, lower bound of sample complexity, to guarantee some true error, right? We require that for any target function concept, there is some function in the hypothesis space our learning algorithm used, which is consistent with all the training set. In other words, for any target function, for any training data, right, you can always find a hypothesis in our hypothesis space such that it can correctly predict every training example, zero training error. So what does this assumption imply? Any suggestion? What does the assumption imply?
There are no errors in your training data?
Yeah, of course. We require there's no error in training data. But this requirement is kind of strong, right? For the concept family, for the family of target functions, we must ensure that for arbitrary target function, you can always find out hypothesis space, find out a candidate function in the hypothesis space which is consistent with any training set. Then what is the relationship between the family of target functions and the hypothesis space which can satisfy this assumption? An idea? So remember, we are trying to learn a family of functions, which we call them concept class, right? The family of functions. And our algorithm will choose a hypothesis space, and our learning is trying to search some function in the hypothesis space, which is as close to the target function as possible. Now, we require that for any target function in this concept class, right? And for any size of training data, we can always find out a candidate function in the hypothesis space which gives zero training error. What does it imply? Any guess? Obviously, this is a very strong assumption. But what does it imply?
So mean your hypothesis space is the same size as the number of possibilities for your data?
Yeah, close. And can it be more in detail?
So there exists a function for every possibility of your.
It's not necessarily that complex. Not necessarily that complex. You can imagine, right? So you can imagine. So there are two sets, right? One set contains all possible target functions. The other set contains all candidate functions. Right? For any target function, we can find out the corresponding candidate function in the hypothesis space that for any training set, their predictions are exactly the same. What does it mean? What? It's not parity. First, if in the extreme you can imagine, right, you can use an arbitrary set of training examples, you require that there is a corresponding function in the hypothesis space, their prediction are the same. What does it mean? It means that in the limit they should be the same. Otherwise, how do you make this guarantee? Right? So remember, this assumption requires that for any. So you can just contain one particular target function. And now I require that on whatever training set, I can find out a hypothesis in the hypothesis space that this candidate gives exactly the same prediction on those training set. So you must, on the extreme, you must ensure that the two functions are exactly the same. Otherwise, you can always find out a set which contains an inconsistent prediction. So that means for any target function, it must belong to the hypothesis space. To fulfill this assumption, right? Any question? Then what does it imply? It implies that your hypothesis space must contain the concept class, right? The family of the target functions. Otherwise, say if some particular target function is outside your hypothesis space, say it stays here, right? And then you must always, it is always possible that you find out a particular example where your target function prediction is different from any predictions from all the functions in H, right? Then you cannot give a zero training error. Any question? Everyone feels good, right? So obviously, this is not very practical. This is a very aggressive assumption. And I remember someone has asked in class, right, it's question whether this assumption is realistic, right? So in practice, we usually never be able to ensure this. Why? Because we even do not know what are particular family of functions, target functions we're looking for. Do you ensure for a particular prediction task, are you sure that your target function or your underlying true function is a linear function or nonlinear function? If it's nonlinear function, what type of nonlinear function? It is, right? Like polynomials or like sine, cosine, or those nonlinear functions without any identical forms? You don't know. In 99% of cases, you don't know. So now that you don't know what is the range of the target functions, or what is the family of target functions be, you cannot guarantee that my hypothesis space is large enough to contain all those unknown target functions. Okay? So a more practical way, a more practical assumption is that we should admit we're trying to learn a concept of target function using the hypothesis space H, but it is possible that the target function does not belong to H. Like here, right? There could be some overlapping between the concept class and the hypothesis space, but you cannot guarantee that all the concepts must belong to the whole hypothesis space. This setting is called agnostic learning. And obviously, this is more practical. So most efforts in computational learning theory is on agnostic learning, rather than those toy problems, where we assume that there are strong classifiers in all kind of situations. And then on the agnostic learning, although we cannot guarantee the concept class is within the whole hypothesis space, we still want to say something about the generalization error, right? The sample complexity. The question is that, can we do it? That's the problem what the agnostic learning wants to address. So everybody is good at the setting of agnostic learning, right? Okay, so the consequence that your target function is not guaranteed to belong to the whole hypothesis space is that you cannot ensure the training error is zero. Right? You cannot ensure the training error is zero. Because suppose there is a target function is outside of hypothesis space, no matter how powerful your learning algorithm is, right, you can always find some mistake in prediction. So your training error cannot be zero. But our goal is still to find a classifier or hypothesis in the hypothesis space that has low training error as well as possible. So what is training error? What is training error?
The error that results from training on the training set, the algorithms.
Yes, yes. So I just want to remind you the definition of training error, because we want to build up a relationship between the training error and test error, or the true error. Right? The training error is the number of wrong predictions in the training set over the total number of training examples. Right? Keep this definition in mind. Why it looks like this? What's wrong? This projector. Okay. So our goal in the learning is still consistent with what we discussed before. Right? We're trying to find a classifier in our hypothesis space which has a low training error, although the found classifier is not necessarily the true target function, right? And what we want in agnostic learning is that we want to find a guarantee. A hypothesis with small training error, note here it's not zero training error, will still have a good accuracy on future same examples. In other words, will still has a low generalization error or true error. And how can we find out this guarantee? We'll use the technique called Q1 to bound the chance that a random variable is far away from its mean. We know that for any random variables from statistical knowledge, they all tend to be close to the mean, right? The closer a random variable is to the closer to the mean, the larger chance the random variables will appear, right? The farther away from the mean, the smaller chance it will appear. Right? And then the natural question would be, like, how can we characterize or how can we find the chance when a random variable is some distance away from its mean? That's what the tail bounds tell us. So so how can we work out those tail bounds? Right? The tail bounds mainly utilize the tails of those distributions. So this is a probability density, right? So you can, from the figure, you know that the chance that a random variable jumps to the distance at this region, right? At this region is actually the area where those tails cover, right? This is the definition of the probability density. So the probability that a particular random variable appears in any region is just the area covered by the densities. Right? Those popular tail bounds are all derived using the tails of the probability densities, and probably in combination with laws of large numbers. So here are a few commonly used tail bounds, and I'm pretty much sure many of you might have met them before, right? Markov's inequality, which can bounce the probability that the non-negative random variable exceeds some fixed value, and a more complex inequality is called Chebyshev inequality, which can bound the probability that the random variable differs from its expected value by more than some fixed number of standard deviations. But those two bounds are not useful in our problem. It's not our focus. Because the reason is that here we want to bound an average of random variables rather than for some particular random variable. The reason why, because we'll discuss in detail later, right? The training error is essentially an average of random variables. And the true error is the expectation of those random variables. So training error is essentially an empirical estimate of the true error. That's why we want to bound the average of random variables. So the particular tail bounds we use here is called Hope-Deans inequality. Hope-Deans inequality has many versions. Right? Here we use this version. It's a simpler version. Right? So this Hope-Dean inequality can upper bounds on how much the average of a set of random variables differs from its expected value by some levels, say epsilon. So here, P denotes the expectation or the mean. And P bar is the average of a set of independent random variables. And the expectation of P bar is P. And expectation of any random variable that is average is P as well. Sorry. P as well. Epsilon is the distance. Is offset where the P bar is from P. And with this Hope-Dean inequality, we can claim that the probability that the expectation is bigger than the average of this set of random variables plus offset epsilon is upper bounded by this exponential term. So we can say in this exponential term, the power is -2 multiplying with the number of the random variables that are averaged at epsilon squared. So you can see that when you increase epsilon, the bounds decays very, very fast, right? Decays in an exponential way and amplified with the square term. Very fast. At the same time, you can see that the more random variables that are averaged, the less likely it will be far away from the expectation, right? Because when we increase the number of random variables that are averaged, this bound decays in an exponential way as well. To give a more detailed description about P and P bar, right? imagine that we have m random variables denoted by x1, x2 to xm, and they are RID, meaning that they are independent and identically distributed. And so P bar is just the average of this x1, x2 to xm, and P is expectation of each random variable. And remember, those random variables are ID, so the expectation are the same, right? And now you just substitute this P and P bar with those formulas, you get a better sense about this inequality, right? And in summary, P here is some true mean. Right? The expectation of the random variable is true mean. Could be like when you cross a ton, what is the probability? You have a heads up, right? And the P bar is actually empirical mean. We know that we want to estimate some true mean. We can just draw a set of independent samples and take an average. That's called empirical estimate. And this bound tells us the empirical mean will not be too far away from the true mean if there are many samples. Any question in understanding this inequality? It's very important. Everyone's good? If you feel any problem, just ask. Don't be shy. Okay, yeah.
What was epsilon again?
Epsilon is just arbitrary distance. Like, say I want to know what's the chance that my average random variables is like 0.1 away from the expectation, right? And I can use this bound to calculate. The chance cannot exceed this bound. Any question? Okay. So now let us look at how can we use this bound to derive the relationship between the training error and the true error. We find that if we consider the true error, that is the generalization error, right, as some true mean, right, we can see that the training error over like m training examples is essentially the empirical estimate of the true error. Now let us think of the definition of the training error again. Right? The definition of training error is the number of wrong predictions on training set over the number of training examples in total. Right? So if you write down this definition like in a mathematical way, it is just like 1 over m. M is the number of training examples, and multiply with a summation. This summation is over all the training examples, and each summand is just a binary indicator. Right? The indicator is 1, meaning that, okay, my prediction is wrong. I had 1, I count 1. Otherwise, if the indicator is 0, meaning that I make a correct prediction. And I just add them together, I know the total number of incorrect predictions, and divide it by the total number of examples, I get my training error. Right? But now let us look at the indicator for each training example. Right? So essentially, this indicator is a binary random variable. So first, y is a random variable. An idea? Y is random variable. No clue? Remember, we don't fix the training data, right? We always assume the training data are randomly collected. That means each training example xi, yi is just random. So the indicator is essentially a function of random variable. A function of random variable is also a random variable. So now let us look at those binary random variables. So what's the expectation of this binary random variable? What is the mean of this binary random variable? So for any binary random variable, the mean is simply the probability that the random variable is 1, right? If you just follow the definition. The expectation is just when the the variable is 1, right? Variable value 1 multiplied with probability plus variable being 0 multiplied with probability. The variable is 0, you multiply whatever, it's just 0, right? So actually, the expectation of a binary random variable is simply the probability that binary random variable hits 1. And what is the probability that this indicator variable being 1? What? Number of what? The probability must be less than 1, right? No, it's not. Obviously, it's not 1/2. If it's 1/2, then we have trouble, right? Your algorithm is not good, right? It is the true error. Why? So we can take a look, right? So what's the definition of the true error? The true error is defined as the probability that our prediction is different from the target's prediction when the input example is sampled from the data underlying data distribution, right? Then when your prediction is wrong, what is the value of the indicator? It's just 1, right? Remember, our indicator is defined here. Only when prediction is inconsistent, the indicator is 1. Otherwise, if you make correct prediction, indicator is 0, right? So that means if and only if your prediction is wrong, your corresponding indicator is 1, right? And the true error is defined as probability that you make wrong prediction. That means it is probability that your indicator is 1. Any questions here? That's the definition. Let's just follow the definition. Still confusing? Okay, so, and second, because all the training examples are sample independent, that means that all those random variables are independent. All those binary indicators are independent, right? So now we can say the training error is an average of set of independent random variables. And the true error is expectation of those random variables. So it's the right fit of the Hopkins inequality. Remember, Hopkins inequality bounds the probability that the true expectation is like epsilon distance away from an average of the random variables. So we can directly apply this Hopkins inequality to the true error and the training error. It's here. So here, true error is the true mean. The expectation of all those binary indicator variables when we compute the training error. And the training error is just an empirical estimate because it is the average of a set of indicator variables. Each indicator is 1 if and only if we make wrong prediction. Otherwise, it's 0. So we can directly apply it. And we found that, okay, the probability that true error is bigger than the training error plus epsilon is less than or equal to exponential to the power of -2 multiplied with the number of training examples multiplied with epsilon squared. That's how we get the relationship between the true error and the empirical error or the training error. Any questions so far? It's just the direct application, all right application of the Hopkins inequality. If you still feel like uncomfortable about how it applies, you just after class you can look at this. You can read these formulas like for 10 times. I'm pretty much sure you will get. Okay, so now from Hopkins inequality, we can think that the probability of a particular hypothesis H has a true error that is more than epsilon away from the training error is bounded about by this exponential term. But this is still not sufficient for us to characterize the performance for a learning algorithm. Why? Because we do not know which particular hypothesis will the learning algorithm return, right? So although the learning algorithm will always find a way to use a way to search a best hypothesis in the whole hypothesis space. Right? But actually, before we run the algorithm, we never know which is the best. The best hypothesis depends on the training set, depends on algorithm design, right? And how can we give a more reliable characterism of generalization performance for a particular learning algorithm? Sorry, I need to change the counter. Any comment? Any suggestion? How can I quantify, or how can we get some guarantee about the performance for a particular learning algorithm rather than particular hypothesis? Think of it. Any idea? Any suggestion? Here's how we do. We use a very conservative, very conservative conclusion. We want to bound the probability that there exists a hypothesis in the whole space such that the true error is bigger than the training error plus epsilon is upper bounded by this term, by some bound, right? So then, whatever way to search for that hypothesis space, right? We can always claim that we have such a good hypothesis. Its true error cannot be too far away from the training error. Then the next question would be, how can we bound this probability? Right? It turns out that we can bound this probability by simply multiplying with the size of hypothesis space with the same exponential term. So now, is everyone comfortable with this? Any questions? And why would we use this rather than this? Again, let me emphasize again, right? Why would we like to use this probability to characterize a performance, a generalization performance for a particular learning algorithm? The reason is that this bound is applied to a single hypothesis. But when you change the training set, when you change the learning algorithms, the algorithm steps, you cannot always guarantee to identify the same hypothesis. We do not know which particular hypothesis the algorithm will finally choose. And then we can only give a more general, more conservative guarantee. That is, we want to know what is the upper bound for the probability that there exists some hypothesis in the whole space which is good enough, meaning that the true error is not too far away from epsilon. We want to bound this probability. If we can claim some very nice bound, very high bound for this probability, then we can say, we can simply say, okay, the whole hypothesis space chosen by this learning algorithm is good. That's the logic we choose to bound this probability. And then the problem is that how can we derive this step, right? So how can we derive this bound by simply multiplying the constant, which is the size of the whole hypothesis space, multiplied with the same exponential term. So this step uses exactly the same trick we used before. That's called union bound, right? So this probability is even, right? There exists some hypothesis such that the true error is epsilon away from the training error, can be decomposed as a union of a set of events, right? The first event will be like the first hypothesis has true error more than epsilon away, right? The second is the second hypothesis which is more than epsilon away, right? And blah 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 until the last hypothesis, which has a true error epsilon away from the training error. So just a union that it is equivalent to this existence statement, right? Now, if you bound this probability for a union of set events, we can just add up the probability of each single event, right? So we did this for homework 1 to prove why this bound is correct. Right? And the probability of each single event is upper bounded exactly by this term. It just adds all the same terms like for many times. The number of the terms is exactly the size of the whole hypothesis space. That's how we end up with this bound. Any questions so far? Everyone's good here, right? Any question? Any question? Okay. So now, from the agnostic learning, we can claim that the probability that exists a hypothesis in the hypothesis space chosen by our learning algorithm, whose true error is epsilon away from the training error, is bounded about by this. And now we can play the same game before. We want this probability to be as small as possible. Say, I want it to be smaller than some designated level, delta. Right? To achieve this, we can simply make this bound less than or equal to delta and solve this inequality in terms of number of training examples. We get our new sample complexity for the agnostic learning. Just solve this inequality. We get this. So now, put them all together. That's the sample complexity for the agnostic learning. So first, an agnostic learner never commit that the target concept must belong to the hypothesis space and does not guarantee zero training error. But we can claim it can guarantee with high probability, 1 minus delta, that the true error is not off by more than epsilon from the training error. Remember, this is talking about the distance between, or the difference between the true error and the training error. If the number of training examples is bigger than this bound. That's how we say something about the agnostic learning. We can now directly say, okay, the generalization error will definitely be less than some level. We can always say, okay, it can be not too far away from the training error with high probability. Obviously, the smaller the training error we get, and you plus them together, we know that, okay, the smaller the training error, the true error you get. So here, let me emphasize again, epsilon is not the absolute level for the true error. It just indicates the difference between the generalization error and the training error. Basically says how much worse will the classifier perform in future than it is in training. And here we still have the terms regarding the size of the whole hypothesis space. That's where Occam's razor shows up again. So for the same epsilon, right, same level, difference level between the training and the true errors, obviously, a classifier with larger hypothesis space will require more training examples to ensure the same difference with high probability, right? So obviously, we still prefer simple models with smaller hypothesis space. The same argument can be applied to agnostic learning. And if we can further fix the number of training examples and then talk about the epsilon, that is the difference between the true error and the training error, that means you just switch the position of epsilon and n, you can get the so-called generalization error bound. So we can claim that if we have m training examples, then with high probability, that is 1 minus delta, the difference between the generalization error and the training error is upper bounded by this term. This term is determined by number of training examples, the size of the hypothesis space, and also the confidence level delta P. So from this bound, what can we observe? Can we observe? Any idea? What can we observe about this generalization error bound? If we have more training examples, what will the bound change? No one answers?
Decrease.
Yeah, you're right? So when you increase number of training examples, this upper bound decreases. And what's the consequence if this upper bound decreases? That means the generalization error is closer to the training error, right? So that is as expected, right? So the more training example you have, then the more close, the more you can expect that the training error is enough to represent your true error. Right? And also, the Occam's razor's principle can be reflected here as well. Yeah.
Sorry. So if you keep increasing your samples, it seems to imply that you will eventually get to zero error. But we were saying specifically that there's a chance that our H, it can be found within our initial hypothesis, right? When it's
You mean which can be found?
So it looks, we're saying specifically that there's going to be a point where the generalization and the training are going to be different, completely different by what, because you can't find
Yes.
that
Yes.
But this says that I keep adding more samples, and eventually I'll get one that does converge to zero. But we're specifically saying you can't. So I guess is this not in the limit? This is just for a smaller set of random.
Of course, if you have an infinite number of samples, you can do that, right? But yeah, but in practice, you cannot get infinite samples.
But even if you have infinite samples, you can't actually learn the target class. Your target class is outside of whatever you can learn. No matter how many samples I throw out, I'm never going to learn, and there's always going to be that error. Right? Or am I?
Yeah, you're right. You're right. But remember, this bound is not only determined by the number of samples. So basically, if you have more and more training examples, at the same time, if the complexity of the model will grow at the same time, most in practice. So that means that this bound is kind of dynamic. It's not fixed, you have a delta and the size of H is fixed. And also, in practice, obviously, what you're saying is right. When M is infinite, and rho of the sample complexity, the rho of the whole, the growth of the hypothesis space is not as fast as the number of samples in the extreme. Yes, it is. The generalization error is the same as training error, but it does not guarantee that your training error is zero. At the most, you can say, okay, my generalization error is the same as the training error, but if your model is not powerful enough, then you still have 10% training error. It's not. That does not mean you learn the target function. Any other question? Okay, so up to now, what we have seen so far include two learning cases or learning settings. The first is called consistent, meaning that okay, our learning algorithm is powerful and our hypothesis space is large enough such that we can always return a hypothesis with zero training error. then we can show that when the number of training examples is bigger than this, and we have high chance to have the true error less than the designated level epsilon. Right? And in agnostic learning, we cannot say the absolute value about the true error. We can only say relatively how far away the true error is from the training error. Right? But we have a similar kind of sample complexity, a low bound. But what is the problem of the results so far? Are they sufficient to characterize all kinds of learning algorithms? Yes, exactly right. So both ones, like although agnostic learning is more practical, right? It's more realistic and more acceptable, but to get a reasonable sample complexity bound, we have to assume that the hypothesis uses always finite. Right? I mentioned the problem before. In many cases, the learning algorithm may use infinite hypothesis space. A typical example is linear classifier. The parameters of linear classifiers are all real values, continuous values. You cannot count the number of distinct continuous values in the whole space. The hypothesis space must be infinite. In that case, we cannot use this bound directly. Because if you use this bound, you say, okay, the number of training examples must be bigger than infinity. And then I can get some guarantee about the generalization error or the difference between the generalization error and true error, the training error. That does not make sense. Then how can we measure the sample complexity? That leads to a new measurement of the model complexity, or the complexity for the hypothesis space. Obviously, we can when the hypothesis space is infinite, you cannot use the size to determine the expressiveness or flexibility or complexity of this hypothesis space, right? Because they are both infinite. They are not comparable, right? But we'll see that even different infinite hypothesis spaces, both they all contain infinite number of functions or candidates. Their expressiveness could be different as well. Think of one linear classification function and a combination of linear classification functions. Which one would you think is more expressive?
Multiple.
Right? Yeah, I think your intuition is right. So can I give a little bit more explanation?
Well, a single linear classifier just creates one type of plane, and that's linear. And then, but if you have multiple combined, you can create much more complicated shapes in the higher dimensional space.
Yeah, correct. Right. Very good. Yes. We mentioned that previously when we do the data boosting. Show examples like we combine a set of linear, just the lines, just a set of lines parallels to the axis, y-axis or x-axis. We'll combine them together. We can form a very complicated classification boundary, right? So obviously, if you just combine a set of linear functions, it must be more expressive than a single classifier. But how can we measure this? How can you use a quantity to differentiate their expressiveness? That is what the Vapnik-Chervonenkis dimension define. It's also short for VC dimension. VC dimension is short for this. So VC dimension was invented to measure the expressive capacity for a set of functions. So a set of functions is just the hypothesis space in machine learning, right? So remember, machine learning is essentially trying to search a function from a set of functions, which is called hypothesis space. The VC dimension can measure the capacity or the expressiveness for this hypothesis space, no matter your hypothesis space is finite or infinite. So you can roughly think it takes the same role as logarithm of size in space. But when the size of hypothesis space is infinitely large, basic dimension is still finite. It's not always finite, but in most cases, it is comparable. You can compare like basic dimensions between different infinite hypothesis spaces. That's the motivation about basic dimension. So to further illustrate why basic dimension is important, so consider a case. I suppose our target function is a rectangle. And how can we classify the points in rectangle with rectangle? Very simple. We classify all the points inside as positive examples and all the points outside as negative examples. And this is our target function. And for this target function, we want to learn a rectangle classifier to be as close to this target function as possible, right? If we start with like 3 examples, obviously our learned rectangle is quite far away from the target rectangle, right? But we can increase between examples. So we say now our learned rectangle classifier is closer, right? And we can increase more, and we get even better rectangle classifier. And now, a natural question would be, when we will continuously to supplement more and more training examples, can we get a guarantee that our learned rectangle will end up with converging to this target rectangle? This is a very natural question. Obviously, when your hypothesis space is finite, using the bound we just mentioned, we can give this guarantee. Because whatever epsilon delta, as long as the number of training examples is bigger than some threshold, you can guarantee this, right? You take a limit, you can ensure that your learned hypothesis converges to the true hypothesis, to the true function, right? But here, the hypothesis space for rectangle classifiers are infinite, right? Remember, a rectangle classifier is determined by 4 points, right? All the 4 points are real values. So in the 2-dimensional space, there are infinite number of rectangles. So can we still get some guarantee? Like when I have more and more training examples, more and more labeled training examples, my learned rectangle is always converging to the target function. This is a natural question we want to ask. But without reasonable definition about the expressiveness of the target of the rectangle hypothesis spaces, we cannot answer this question because all the bounds previously used is not applicable here. So now let us talk about how basic dimension defines the expressiveness of a set of infinite functions. High dimensional means that the number of features or the number of attributes used is are many. You have 10 features, so you are dealing with 10-dimensional input vectors. You have like 1 million features, your input vectors is 1 million dimension. That's high dimensional space. Any questions so far? Okay, so and for this more flexible interval hypothesis spaces, right? We know we can verify that all sets of 1 or 2 points can be shattered by interval hypothesis space. But for sets of 3 points, they cannot be shattered. But obviously, it is better than left bounded interval, right? And here you should be aware that both the free interval hypothesis space and the left bounded interval hypothesis space, they're infinite. So you cannot compare their expressiveness in terms of size of the whole hypothesis space. Both are infinite. But through the number of shattering points, you can see the distinction in terms of expressiveness. So now let us look at the third example is linear function in two-dimensional space is also called half spaces. Half spaces meaning that, okay, if I perform linear classifier, I perform linear classification in the plane. So let's ask how many points the linear classifier in the plane can most shatter. So can they shatter just one point? Yes, obviously, right? So can they shatter 2 points? Yeah, the example just talk about, just show the example, show the case, right? For 2 points, we have like a 4 labeling assignment. For each labeling assignment, we'll have a classifier which separates positive and negative example. Then the question is, how about 3 points? We know, okay, the left bounded intervals and free intervals, they both cannot shatter like 3 points. And then how about linear classifiers? Again, to verify whether they can be shattered by a linear classifier, we need to enumerate all possible labelings for the 3 points. How many possible labelings for the 3 points? How many? So each point can have at most 2 labels, right? And then for 3 points, how many labels in total? 2 to the 3, right? 8. So to verify this, you need to do a little bit, a bit more like tedious work. You need to enumerate all the 8 possible labelings and say whether for each labeling we can find a classifier correctly predicting every example. And fortunately, yes, we can do it.
What if your 3 points are in a line?
That's a very good question. Yeah, here we only care about if there exist 3 points, distinct points, they can be shattered or not. We do not care about like it must shatter like 3 points in whatever displacements of these points.
Doesn't that defeat the purpose of having to enumerate all possible combinations of them, though? You say what you just said again?
I mean, for this particular 3 points, right? If you want to justify whether it can be shattered by the linear classifiers, you need to enumerate all possible labels of the 3 points, right?
All labels,
Not positions. You cannot enumerate all possible positions. There are infinite many possible positions. So what we care about, like, can you find out a particular set of positions, and for all possible labels can be shattered, right? This currently we're talking about. And later we'll explain why. We do not care about positions. And then the next question is that, do we have some 4 points which can be shattered by the linear classifiers? Give me a guess. Why? And I think you hit the key point. I won't go through into the detail. This is a homework problem. If you look into the homework problem, this is the problem you need to address yourself. So basically, doing shattering is like an adversary game. You want to claim that your hypothesis space is expressive enough such that it can shatter whatever, like D points, right? And then there is an adversary who wants to beat you, and here just provide some hard, evil labeling to you. And then your job is to find a function in your hypothesis space that can correctly predict this evil labeling. And then the adversary will try to find an even harder labeling and throw it back to you. And do it back and forth and forth. If the adversary finally it enumerates all possible labels, and you'll end up with finding every classification function give perfect predictions. You win. Otherwise, you fail, and we cannot claim the hypothesis space can shatter these d-plots. This is the basic of how we verify shattering. And if your hypothesis space is so expressive such that for arbitrarily large finite subsets of instance space X, they can be shattered by your hypothesis space. That actually implies your hypothesis space can shatter infinite points. And that sounds surprising, but there is such kind of hypothesis space. And we'll give an example later. And when your hypothesis space can shatter the entire instance space X, if your instance space X is finite, that means it shatters finite instance space. If your instance space is infinite, that means it shatters the infinite points. Then we say your hypothesis space is unbiased. So obviously, it's very hard to let your hypothesis space be unbiased. Right? But we can see that the larger the subset of the instance space that can be shattered, the more expressive your hypothesis space H is. Any questions so far? Okay, so now comes to our definition of VC dimension. So the VC dimension of a hypothesis space H over the instance space X is the size of the largest finite subset of X that can be shattered by H. So actually shattering is the key concept, is a key component for the VC dimension. So to calculate VC dimension, we just enumerate the size of the number of points. Right? You can start with 1 point and say whether it can shatter, and 2 points whether it can be shattered. If there exists any subset of size d that can be shattered, then we claim that VC dimension is no less than d. Here, there exists any subset. We do not require, like, for an arbitrary subset of size d, it must be shattered. As long as we can find out a set of d points that can be shattered, we can claim our VC dimension is no less than d. But if there is no subset of size d can be shattered, then VC dimension must be less than d. That's the definition of VC dimension. Basically, is a maximum size of points that can be shattered by your hypothesis space H. This is called VC dimension. And here, just to give you a few results of VC dimension for different hypothesis spaces, right? Half intervals, as we just mentioned, VC dimension is 1 because it cannot shatter 2 points, right? And free intervals, 2 points. We show that for any 3 points, they cannot be shattered. And for half spaces, the answer is 3. So I tell you half the answer of that homework problem. 4 points cannot be shattered. Any 4 points cannot be shattered by the linear classifiers. Then it's your task to show that. And in general, the VC dimension for a linear classifier in the d-dimensional space is d plus 1. And the VC dimension for neural networks is number of parameters. So don't ask me how to prove this. Definitely we cannot enumerate by our hand. We use other method. And here is the particular power of hypothesis space. It's called 1 nearest neighbors. And the VC dimension is infinite. It's kind of like surprising, right? One nearest neighbor classifier might be the simplest classifier ever. Right? Giving you a training set, you just you want to predict any example, just search for the training set, which one is the closest to it, and pick the example of that. You pick the label of that example. That is called one use table. But this dimension is integer. So now we have introduced the concept of this dimension, and it is motivated from the sample complexity for consistent learners and final hypothesis space. We found that the sample complexity depends on the log of size of the space, which is not practical enough because many learning algorithms require infinite hypothesis space. Then we need a new measurement of the expressiveness or flexibility of your hypothesis space. That leads to the invention of the BC dimension. So we can consider this dimension behaves like logarithm size of this space. Okay, so let us continue on next one.